Hello guys, welcome back on Tesla Adventures. Today in this video we'll discuss about elasticity, and in this chapter we'll discuss about the elastic properties of matter. So starting from the elasticity, we can say that in each solid atom or in each solid crystal, you can see that atoms are arranged in such a way such that they are at crystal lattice points, and each atom is connected to the neighboring atom with some inter or intramolecular forces. So those forces are keeping those atoms stable at their lattice positions, and the complete crystal is in equilibrium. But when we deform that matter, then due to deformation, the intermolecular or interatomic distance between those atoms and molecules decrease or increase, and due to that change in the interatomic configuration, those atoms and molecules tends to regain their original position when the deformation force is removed. So this property of the matter, in fact, we are not only concerned about the solids. In fact, elasticity is the property of matter, which is elasticity is also seen in fluids. So, but for the primary basis, we are defining the elasticity from solids. So the property of the matter, by virtue of which that matter tries to regain its original shape and size when the deforming force is being removed, is called as elasticity. And most of the kids are confused with the term elasticity, and they assume that if we stretch a rubber band, and if we stretch two different types of rubber band, and one is easily stretchable and the other one is somewhat rigid, it is not easily stretchable. So they assume that the rubber band which is easily stretchable is more elastic. In fact, if we compare a spring of a pen and if we compare a shocker spring of any railway coach or any vehicle, then we know that it is stiffer. Shocker spring is stiffer as compared to the spring of the pen. So we can say that it is very difficult to deform a shocker spring as compared to the spring of the pen. So in reality, the more elastic will be the shocker spring. So what does the elasticity means? So when we deform any matter, then a restoring force is developed in it, which tends to bring back that body or that matter into its original shape or size. So the amount of that restoring force developed will be proportional to the elasticity of that body. More elastic body will have more restoring force developed in it. And in fact, we can say that more elastic body will oppose any deformation applied on it. So we have compared a spring of pen and we have compared a spring of shocker. So we can say that shocker spring will oppose the deforming force more as compared to the pen spring. So the more elastic will be the shocker spring. So it is very important you to visualize that the material which is very hard to deform will be more elastic, and we know that nothing in this universe, no element is perfectly elastic till now. So all the elements are somewhat elastic, but the elements which oppose their change in deformation are more elastic, as the deforming force is proportional to the elasticity. Now what is deforming force? As we have already discussed, then when matter is deformed from its original shape or size, then a force is developed in it which tries to regain that matter to its original shape and size. That force is called as deforming force. And perfectly elastic body, that body which regains its original shape and size 100%, after removal of the deforming force is called as perfectly elastic body. For example, quartz and the phosphorus bronze wire, which is used in making the moving coil galvanometer also, are perfectly elastic bodies. And perfectly plastic body is a body which does the opposite work, which means that when we deform that body, which is a perfectly plastic body, and when the deformation force is removed, then that body does not regains its original shape or size at all, and howsoever be the smallest force applied on it, so it will not regain its original shape and size at all. Okay, now we will study elasticity more with the help of some physical quantities like stress and strain. So first of all, we define stress. That is, when a body is deformed, then some restoring force is developed in it. We have already discussed this fact, and this restoring force brings back that body to its original shape and size. So the restoring force developed in that body per unit area of cross section is called as the stress developed in that body. So there are basically three types of stress. This is longitudinal stress, and the second one is shear stress or tangential stress, and the third one is volumetric stress. We'll discuss one by one. So longitudinal stress is the stress developed in a body when its length changes. So you can see that this is a piece of a wire or a rod, and this is a tensile force which is stretching this wire. So when this force stretches this wire by a length of delta L, then a restoring force is developed in opposite direction, just in downward direction. That restoring force per unit area is called as tensile stress. And when this body or this wire or this rod is compressed by some force, then a restoring force is developed in it, which is just in the opposite direction of this external force. So this restoring force per unit this cross section area is called as compressive stress. You should also know that in numerical calculations we will use this external force as the restoring force only, because this extension or compression is so small, or it is infinitely slow at pace, so that we can say that net force acting on the body at each time is zero. What does I mean to say? That when we apply this force to deform the body, then we deform this body infinitely slowly, which means that at each moment of time the net force acting on this body is zero. Okay, so net force is zero on the body as well as on each cross section, because on each cross section external force is opposing the equal deforming force. So when we write down the stress, we will write the restoring force per unit area, but we know that the magnitude of restoring force is exactly equal to the external force. So we will use the magnitude of external force for calculation of stress instead of restoring force, considering the fact that they are equal in magnitude. Okay, now you can imagine that there is a box. We can see that this type of box is a box in which your TV is being packed, which we call as carton, and some mud is being filled in that box so that its base is immovable. Now if we apply some tangential force on the top of that carton box, then that force will deform the box in this shown in this figure. So the top face of this box will be displaced as compared to the bottom face, which is stationary, and this displacement is delta x. This height will be L, and for small displacements we can say that the stress F will be equal to, tangential stress will be equal to F upon the area on which we have applied the force. Okay, so this is shear or tangential stress. Now, what is volumetric stress? So, volumetric stress is sometimes also called as pressure. So, when we apply some pressure uniformly on a body which is either solid or fluid, then it changes its shape and size, and that pressure, which is the force per unit area, is called as volumetric stress. So volumetric stress is F perpendicular upon area, and you should also remember that volumetric stress can be called as pressure also, and the dimensions of stress are equal to pressure. Okay, now what is strain? So when a body is deformed from its original shape or size, then the fractional change in its dimensions is called a strain. Now what do I mean with the fractional change? I mean that let's suppose this is a rod or a wire which is being pulled or compressed by a length of delta L, and L0 is the original length of this rod. So the longitudinal strain which will be developed in this rod will be delta L upon L0. This is L0, where L0 will be the original length and delta L is the change in length. So you can see that as stress is the ratio of the dimensions, so dimensionally stress has no dimension, and the unit of stress is nothing. So we can say that stress is unitless, but in fact strain is unitless, but stress has the dimension of pressure. Now we talk about the tangential or shear strain. Now this shear strain, this is in fact strain. So this shear strain is this delta x displacement of the upper face as compared to the lower face divided by this length L. So this is delta x upon L, and this is equal to tan theta, and for small displacements we know that tan theta is equal to theta approximately. So this theta is called as shear strain. Now volumetric strain is obviously the change in volume upon the original volume. This is the volumetric strain. So this video has the basic idea about elasticity, stress and strain, and let me recap all of those three quantities. That elasticity is a property of a body. How it is not necessary that elasticity is defined only for solids. In fact, elasticity is a property of matter. So elasticity can be seen in fluids also, and it is a property by which that matter, when deformed from its original shape or size, tries to regain its original shape or size when deforming force is removed. This inherent property of is called as elasticity. So we will also discuss that why elasticity occurs, why that property is generated in the body in the upcoming videos. Now what is strain? So when we deform a body by some deforming force, then some restoring force is developed in that body, and that restoring force per unit area is called as stress developed in that body. So stress is in fact, you should also know that stress is not the applied force per unit area, but numerically we always consider that applied force is equal to the restoring force developed. So numerically we will take the restoring force equal to the external applied force. So that doesn't mean that we are defining stress as external force per unit area. In fact, stress is a restoring force per unit area developed in a body when it is being deformed. So, stress is also of three types. It is longitudinal stress, shear stress, and volumetric stress. Now we move on to the strain quickly. And strain, when a body is deformed, then strain is the fractional change in its dimensions, which means that when its length is deformed, then change in length upon original length is the longitudinal strain. And when the body is deformed like that, then the shear strain is this angle tan theta, which is delta x by L. And when the volume of the body is deformed, then the volumetric strain is delta V by V. So this was the quick recap of the lecture, and in the next video we'll discuss the Hooke's law in detail and the potential energy view of elasticity. Thank you.